Here it is, lecture number 9. And what follows today is that we will discuss more details about how is that we can model the hydraulics. And today, the particular emphasis is in this lump fluid theory, the one that I just mentioned before I got started today. So this is the main body of today's lecture. I hope we have a time to discuss about the different flow types as well, but we'll see. We'll see. Lump fluid theory is like an essence of the hydraulic modeling. So this, if you know the lump fluid theory, then you pretty much know everything that you need to know. So this is why today's lecture is extremely, extremely important. Okay, so then there was a questions about equation of motion in embedded technique represented by static equilibrium. Okay. Okay, so lecture PDF is not yet updated. Okay, this is something that I'm not sure what you guys are discussing. We need to get back to that topic in Teams meeting right after this lecture. So some of the things that regarding the PDF and things related to static equilibrium, I'm not 100% sure what is that you guys are referring to. So please see me in a team session right after today's lecture. Anyways, so today we finalized the case of properties of fluids, and we already learned that there's two properties that are important. One is a bulk modulus, and another is viscosity. And we already covered the bulk modulus. What is left is viscosity, and that's what we're going to cover today. So that's what's going to follow. But before we jumping into today's topic, let me summarize what is that we discussed last week. Well, first of all, I shortly mentioned last week that you guys need to be familiar with the drawing symbols associated to hydraulics. So what I mean about that, I mean this, this is how the hydraulic circuit look in real life. In this hydraulic circuit, we have the hydraulic cylinder here, and the drawing symbol for a hydraulic cylinder is the one that is shown here. So to understand how the hydraulic is modeled and how is it operates, you have to be able to understand these drawing symbols. The hydraulic cylinder is very obvious, so there's no difficulties to understand that. But then if we're going to take another end of the hydraulic circuit, which is this one here, this is a tank connected to pump, which is then operated by a motor. These drawing symbols are something that are not well describing how is it they look in the real life. Ah, okay, now I know. So you guys are saying that last week PowerPoint presentation is not yet uploaded to Moodle. My apologies. So my mistake. Somehow I don't understand how that is possible, because I usually keep it in my rhythm such the way that as the first thing on Thursday morning, I'm editing my lecture. I don't know if you guys recognize, but I'm doing a little bit of editing, not serious editing, but I just take the part of the streaming that I'm saying nothing off, and then that's my editing, and I'm uploading the PDF. So obviously I had something wrong in my brain because I have not made it. So my apology. Sorry about that. Back to the drawing symbols. So this is how the tank look in the real life, which is usually a big chunk of like rectangular or this box-like body. Dimensions could be 1 meter times half a meter times half a meter. It really depends on the application. Its drawing symbol is this one. This is a tank. Pump's drawing symbol is this one here, and then the motor is here. And now this pump here is a fixed volume pump, meaning that it's also always keep on introducing the flow and energy to the system regardless if it is needed or not. And this is one of the basics, very conventional pumps, but the ones that are more used at the moment, because energy is something that we don't want to waste. So you can use these variable volume pumps, and then the drawing symbol is such that maybe it's not no longer clear for you, but there's like arrow, cross it over the pump, and so on and so forth. Then we have this pressure relief pump, pressure relief valve, some kind of filter here. These are how they look in the real life, and this is how they look in the drawing symbols. This is a direction valve. Direction valve is here, and is operated by a shaft, so it's mechanically operated, which you really don't see much these days. Typically, these valves are operated by, well, typically they're operated by magnets, something electronic also. So this kind of mechanical connections are not typically used anymore. Anyway, so this shaft here, which is a little bit visible here, is moving the spool, which is the one that is on here, back and forth. And that's how you can connect the different boards together. These boards in this system, there is a total of 4 boards. And these are the whole thing. So this is how this look. So if you are not familiar with the drawing symbols, make sure you can take yourself to another YouTube channel and learn about these symbols. Okay, so that's what we discussed. And we discussed about the big picture. The big picture is this, that roughly speaking, we focus in the first period this box that is red in a color, which is a mechanical modeling. And we know that the mechanical structure, as a mechanical structure, is not really a machine yet. And because it's missing the motion. And motion can be introduced, by a different kind of actuators. And these actuators can be electric drives, pneumatics, water hydraulics, and others, or pneumatics, or hydraulics, just the conventional hydraulics. Important thing is that to be able to understand the full dynamic behavior of the machine, like this kind of crane here, you need to analyze the structure, which is a combination of mechanical structure and actuators, because they are assembled in a real life. And you see that there's a hydraulic cylinder here, and this is the one that is introduced in the lift motion. Tilt motion, that too is introduced by hydraulic cylinder. So now to understand what's going on in terms of dynamics of this machine, you need to understand hydraulics and mechanics. That's why we are now looking this particular box here. I don't remember if I explained about the water hydraulics last week, but the water hydraulics was something. I cannot say that is anymore something, but it was something that was very much in fashion a while ago, because hydraulics is very, very conventional field, and the developments you can see in hydraulics are next to nothing. Within the 50 years or something, there is no significant developments in hydraulics. There's certain things that are related to pump technology, a little bit about how the spool is controlled by magnets and so on and so forth. But the big picture is still the same. The big picture is such that you're introducing pressure losses to control the hydraulics, which is a big problem because the pressure losses are energy losses as well. And we don't want to waste energy, like I said in the beginning. So the developments related to hydraulics are not significant. There is recently something that is interesting, a little bit promising too. It is called digital hydraulics. That I'm going to explain to you next week. But the water hydraulics, that was very much in fashion a while ago, because problem in the hydraulics is that whatever you have a hydraulics, you have also a little bit of leakage. And if guys, so do me a favor. So if I have mentioned this story to you last week, can you please let me know that in a chat window, because my memory is good, but it's short. And maybe I already made several times the stories to you such the way that I have repeated them. I don't remember. I don't remember that, but if you have heard about the story of water hydraulics, just send a message to chat window that been there, done that. Okay, so water hydraulics was something very fashionable a little while ago because of this environmental aspect. So whenever you have a hydraulics, you have leakage. That's like almost like a rule of thumb. It's not that big problem as it used to be, but still the hydraulics is nasty because, conventional hydraulics, I mean, because in a conventional hydraulics, you have high pressures, 200 bars more, and those are the hose connections and connections that are vulnerable for leakage. And that makes things looking really bad because even a little bit, a small amount of oil in your machine make it look like old rusty machine. So it's not looking great and it's environmentally very unpleasant as well. So easy solution is to replace oil by water. Yeah, makes sense. Problem is this, that the water hydraulics tend to be way more expensive than conventional hydraulics. And the reason is the fact that the water is not so great lubricant. Even though that there is a phrase which says that the water is the best lubricant. At least this is in the Finnish language, probably in English too. But in real life, water is not a great lubricant at all, particularly when comparing that to oil. And because of the low lubricability ability, you have to use some exotic materials in your water hydraulic components, just like ceramics and such, which makes them to be expensive. So it's not as affordable as a conventional hydraulics. And it comes with another drawback too. That's the fact that if you take water, you put it in a container, like you put the water to this cup, you leave the water to your cup for, I don't know, next 6 months or so, and you come back, the water is no longer there. I mean, the water is there, but it also, comes along with the green monsters. So it's all kind of nasty stuff that is growing in your water. So you need to get rid of those nasty monsters, these green monsters. And the easiest way to do that is to put a little bit of poison to your water. So then forget about the environmental aspect if you do so. So that's why, because of money involved to water hydraulics, because environmental aspects are like questionable a little bit. So the water hydraulics is not that heavily used at the moment. There is, however, major trend. Yeah, I'm sorry that I'm a little bit of sidetrack here, but I soon will be back to the modeling business. There is a high trend here to replace the hydraulics by electric drives. This you can see, particularly you can see that in industrial applications, such like, well, the machines that I use in wood processing industry, paper making machines and such. There is cases where you can actually take a hydraulic off and replace the hydraulic by electric drives. This is a trend that at least I can see is a growing trend. Anyways, we here are modeling hydraulics because even though that is a conventional, kind of like not so advanced technology, it's still very much used technology because of the power density is so high, like I mentioned last week. Now that's what we're going to focus this semester, this period, sorry. Control system, we're going to discuss a little bit about users. We definitely will discuss about that when it's a time to look at the gamification concepts and then the working process, which depends heavily on your application. We're going to discuss about that too a bit later. All right, properties of fluid. I mentioned already that there's two properties that are important, viscosity and bulk modulus. We already discussed that the bulk modulus is something that is more important, way more, having way more higher practical value than the viscosity, because viscosity, theoretically speaking, only affects to flows that are laminar in nature, which is not the usual case, so it's unusual case. Okay, so bulk modulus and viscosity. We learned that the bulk modulus is something that is describing, and listen to me here, because my first in-class quiz is exactly this. So the bulk modulus is describing the flexibility of hydraulics. Put it in a writing. Write that bulk modulus is describing flexibility because that's what I'm about to ask. Then those of you that are actually following me and not following on Netflix or, I don't know, other channels in YouTube, you can go and look yourself to Socrative. Their first in-class quiz is on. And in that first in-class quiz, I'm asking, the question reads like this. bulk modulus in hydraulics describes. And then the options are force produced by a cylinder, flexibility, compressibility of hydraulics, oil amount in the circuit, number of components in a hydraulic circuit. So that's about it. So how common is a hydraulic accidents? Well, depending how you're defining the accident. The kind of like and the game is on. The game is not yet. Don't release this information to those ones that are putting their attention to someplace else. So back to first comment. It's common that you have malfunction in problems in hydraulics. A typical problem is that in mobile machinery where the hydraulics is heavily used, you have this hose connection, which is that rubber connection between the components. And these hoses tend to break. And that causes the situation that you have a case that the oil goes off from your system. Of course, you can turn out your diesel engine, which turns off the pump, and then you can get rid of the oil running out of from your system. But that can introduce some dangerous scenarios. So it's something that is good to keep in, or good to take into account. In the critical applications, there is usually something that is called counterbalance valve, which avoids the situation that drinks are rapidly coming down. But a good question, and my answer to you is that my small accidents happens all the time. I was here in a bulk modulus. So the bulk modulus takes account the flexibility of hydraulics. And also something that affects the flexibility is a stiffness of different components and amount of dissolved air. And when you put all these effects together, then you can get something that is called effective bulk modulus. And that you can compute by using this equation. And what is that we have in this equation? We have here a flexibility of fluid. Then we have here flexibility of the container, whatever that may be in a physical system. Volume associated to that particular component. Excuse me, this is the total volume of the system, volume associated to that component. And the second container and the dissolved air. That's how it goes. Okay, properties of fluids. So before we're looking at the final things about properties of fluids, so let me tell you something which you do need when answering this weekly homework. So this weekly homework, I'm asking you to evaluate the natural frequency associated to system where there is a hydraulic involved, and the mechanical components are assumed to be rigid, which we don't know that you really don't find that kind of rigid components in the real life. Oh yeah, well this is a nice comment, but another comment here about power steering in cars. Yeah, that I really am not that much in the car business, but I trust that this is the case, that the power steering system are replaced by electrical systems instead of hydraulics. Again, I really don't know. I'm more like a motorcycle person rather than a car guy, so I cannot really tell how are the trends related to new cars. My car is like all like no limit, so I guess no power steering system whatsoever. I guess, I don't know. Okay. So about this stiffness of hydraulics. So basically when you have this kind of two-way hydraulic cylinder, kind of like how it looked mechanically. Oh, I'm sorry, I'm blocking the view, so I need to make another cylinder here. So this is my piston. Piston rod is this one, and the piston is here. This is the cylinder. So like an analytical representation of bulk modulus is that there is a spring here and two springs here, or one spring, however you wanted to say. But these springs are introducing the flexibility associated with this hydraulic cylinder. And there are cases that this flexibility is more significant than the mechanical flexibility because of the deformation of bodies. Okay, how is it you can compute the natural frequency of the system like this? The natural frequency, this I think that they already explained in junior high school, in elementary school, that the natural frequency can be computed in such a way that is square root stiffness divided by mass. Okay, we know mass. This is our mass. So only thing that we do not know this time is how is a stiffness. So how is a definition of stiffness then? This is how is a change of the force with respect to change of the displacement. That's the definition of stiffness. Okay, so let's start looking these things. How is it we can compute the change of the force? Force affecting here are, of course, how much the pressure is affecting the piston side here and piston rod side here. So those are the two forces that are applying, and they are opposite in direction. Okay, this one here is a piston side, so it's a P2, change of the pressure to be more specific, multiplied by corresponding cross-section area, and then minus this pressure here, which is the one shown here, and then multiplied by cross-section area, this one here. So this is a change of the force. Change of the displacement is this one here. So the change of the displacement goes such the way that you have here volume change divided by corresponding cross-section area, and the volume change here divided by corresponding cross-section area. So now, when you substitute in that information, this one here, this one here, you can get this stiffness as it is shown here. And then we're going to use the definition of bulk modulus, the one we learned last week. And by using that definition of bulk modulus, we can play the relation between the bulk modulus and the volume, such that there is the pressure difference and the volume difference. And now when using this information, the stiffness finally can be computed as it is shown here. So this is it. So now you know you have everything you need to know in this example, or how to solve this example. So it goes such the way again that here is your natural, or how you can compute the omega of the structure. That's the stiffness divided by mass, and that's how it goes. This is your stiffness. Mass is the one that is shown here. So not too complicated at all. And now comes this big surprise thing, which I don't think you can believe your eyes. So first in class quiz. Force produced by a cylinder. Excuse me. I did not read the question. So bulk models in hydraulics describes force produced by a cylinder, flexibility, compressibility of hydraulics, oil amount in the circuit, number of components in hydraulic circuit. So those are the four choices, and I can see that I already have 50 answers in my system. And when I'm looking my YouTube studio, I can see that I have 53, I guess 53 viewers. I guess so. So I'm expecting, okay, now I got 55 answers, and I think this is pretty much it. So let me take a look at the in-class quizzes. I mean, how the game is on. So we have a lot of 100%. We have a lot of 97%, 93%, 93%, 96%, 95%, 92%, 100%. Okay, so, and I got 57 answers, which is more than last week, if I remember correctly. So my personal guess is 85%. We'll see this. We'll see how it's going to be very soon. Oh, now the last ones are still entering the answer to the system. So I'm gonna close this right now. And because of the delay, make sure you do your answering or you enter your answer right now. Okay, so here it is. And the success rate today is here it is. Look at this. And no, do nothing. Do nothing. Absolutely. Those ones that I have not entered the answer to system, do nothing. And let's take a, well, I don't know, what is a proper way to celebrate this? So we scored 100%. Look at this. So I was all the time wrong with my kind of like my hypothesis that some of you are never ever watching me and never ever listen me, and you just watching I don't know, Netflix series or something else, whatever there's in class quiz, you just guess something, and I was wrong. My apology. My apology. Whoa, this is awesome thing. So it happened. It happened. How is that? Yeah, now dance. Now dance and the multi-body song. Well, I cannot do the multi-body song anymore because we are no longer in a subject matter of the multi-body. So it needs to be hydraulics related, hydraulic modeling related song, which I don't know any. So that's about it. So very nice, very nice. I'm so proud of you guys. So I don't know. So and myself too. So this makes myself like the best teacher ever. I think that's what this is a kind of the recognition that I'm gonna give myself. Nice. Oh my God! Look at this. Look at this. Now it did prove that my hypothesis was correct. So take a look at what's in Socrates window. So the success rate is no longer 100%, but the 98%. So that's about it. Oh, that's a big relief because I have, the dance. I was not prepared to do the dancing today. So lucky me, I guess. Okay, now back to my explanation. Now I'm going to speed up a little bit because I see that for some reason I've been very, very slow today. So let me speed up and explain the something which is not the side topic. Yeah, I think that I'm gonna. Yeah, I'm so happy that you scored 100%. So I really don't care about who was the one that came late and then they were answering correctly. Yeah, yeah, but I'm not gonna dance. Not gonna dance because of the last. Oh, you set the ball about the dancing. No, I'm not gonna watch that. Okay, okay, forget about it. No dancing today. No dancing. And now you make me confused. So I got completely confused. Like, what is that I would like to do here? So no, it wasn't, and it wasn't me that entered this incorrect answer. It wasn't definitely me. My hands was visible all the time, all the time. Okay, viscosity. So it's so hard to focus on this, but let me do my best. Viscosity. Short explanation, and now this is blocking my view. So hold on. Here. Okay, viscosity. I'm not going to take a look at this chat window for a little while because I need to kind of collect my thoughts. Then I'm going to take a later about your ideas about the dancing, but not this time. Okay, let's make an experiment here. And in this experiment, I want to define the viscosity. So viscosity is the one that again affects whenever there's a laminar flow. All right. So in this experiment, I have a plate, this one here, and I'm moving the plate by using a force that is capable to introduce the velocity v to this plate. Okay, so the plate is moving to right-hand side direction in velocity v. This plate is having the cross-section area facing towards this fluid, film fluid, or the oil that is standing here. And cross-section area is called A. And the distance from this plate to, the crown, which is standing still, then this distance is called as a Y. So there's a thin layer of oil, and this plate is traveling on top of the thin layer of the oil. And what happens when you do that? When you have a Newtonian kind of fluids, and all the fluids we deal with in the hydraulics are that kind of the fluids, particle velocity will be distributed along, or pretty much shown in this picture here. So the particles that are next to this crown that is not moving anywhere, their velocity is 0. Whereas the particles that are next to this plate, their velocity is exactly the same velocity than the plate. And the rest of the particles, their velocity is roughly linearly distributed. And that's about what's going to happen. Now what we're going to do here is that we're going to define this viscosity. The viscosity is kind of something that defines the internal friction between the fluid layers. So pretty much because of this velocity distribution, so they have to be internal friction shear force that is introducing this kind of velocity difference. And this velocity difference is the one that is giving us a definition of viscosity. Okay. Now, force that is needed to do this experiment can be expressed such the way that is this cross-section area of the plate, of course. Then something that is called absolute velocity. And this is that definition of, how is a friction within this fluid. And then we have the velocity here, and how is a layer, how thick is a layer of the oil. So this is our setup here. Now, with this setup, I'm going to use a definition of shear force, which is shear force, shear equal to the force divided by corresponding cross-section area. Now, using this definition, I'm going to get this shear distribution or shear in this setup. And now the one that I would really, what I'm after here, is this one here. This absolute viscosity. Absolute viscosity, they're telling a little bit about how are the property, this viscosity property of this particular oil here, fluid. And now this absolute viscosity is typically not the one that is used, but the one that is typically used is something called kinematic viscosity. And you can move from absolute viscosity to kinematic viscosity by defining the absolute viscosity by density. When you do that, that's going to be your kinematic viscosity. And this is the one that is then used in a computation. In SI units, viscosity is having this meter power 2 divided by seconds. That's its units. But quite often, something that you can see in a real life is centistrokes. And something that you can see often is this abbreviation that's coming from the Society of Automobile Engineers. And typically when you purchase an oil that goes to your car, this is the one that you can see. This abbreviation, Society of Automobile Engineering. Modeling perspective, viscosity is a very problematic. And it's very problematic because it depends on many things. These figures that is here in the right, they're showing a little bit about how much viscosity is a function of temperature. And it's so heavily a function of the temperature that you need to use a logarithmic scale to explain it. So here is a typical oil. And you see that the temperature when it's ranging from minus 20 to 100 degrees, this is in degrees, it's a huge drop in the viscosity. And when you look at how much viscosity is a function of the pressure, you can see that too is something that is ranging significantly. This you can see in a different temperature, different pressures, and again you need to use a logarithmic scale because the effect is so significant. In real life, in modeling life, No, we are not going to take this into account. So we need to select the viscosity that is constant, which is a huge assumption because look at how much it is changing and ranging because of the temperature. But again, when we do the modeling, we don't take this into account. We're just going to select the value, one value, this kind of table or other tables, and assuming that the temperature remaining constant during the simulation, which may not be the case. May not be the case. Okay, so dancing thing. Maybe that let me think about this. Last lecture, as I promised, that it's going to be face-to-face lecture. I hope that it's not going to be mass-to-mass lecture, but the face-to-face lecture. I'm going to think about the dancing thing, and maybe we can celebrate this 100% success rate in the last lecture. Hope you agree with that. So no dancing today. Problem in dancing today is that this goes to YouTube, and I can easily make myself looking stupid. If I can make it make that more than I'm already doing. I really don't know. Anyways, so let's continue. Lamp fluid theory. As promised, this is going to be the main body of today's lecture. And I'm running late today. For some reason, I'm slow. So I need to apologize that. Lamp fluid theory, that's essence of hydraulic modeling. What is the deal with that? Well, here's a little bit of explanation that I have put it in our writing. So this is the one, this lamp fluid theory is the one that is used to compute the pressures in different locations of the hydraulic circuit. And it's made in such a way that I'm kind of first dividing my hydraulic circuit within the volumes where I'm assumed to be pressure to be equally distributed. I'm going to repeat this in a moment because this is something that is important you to understand. And then once I do that, then I'm computing the pressures as a function of time. So it means that this procedure, this method based on lamp fluid theory, cannot take the acoustic pressure waves into account because we computed the pressure only one location within the one volume. All right. So the pressure waves that are traveling back and forth, those are the ones that we cannot take into account, which is a drawback in certain application, but most of the cases, when looking at the mobile machinery, industrial application even more. Okay, this is where I need to take back. So in industrial applications, it could be a bit more significant drawback. But in the mobile machinery, pipelines are fairly short and work cycles are relatively slow. So these pressure waves are not the big problem, typically. If they are a problem, then you cannot really tackle them by using this modeling technique. But anyways, so let me, okay, why is it this guy is not willing to, oh, I guess that my PowerPoint is not responding. And now it is responding again. Okay, in the lamp fluid theory, like I said, we're going to divide the hydraulic circuit within, well, to volumes where we assume the pressure to be equally distributed. So the pressure, within the container or within the volume is assumed to be constant all over. So it's not constant as a function of time, but if I have, let's say, if I'm going to make like hydraulic cylinder like this, I'm assuming that the pressure in this corner here is same as the pressure in that corner. That's what it's standing for. That's what I would like to say here. And once we do this division, then we're going to derive the differential equations, which is a first order differential equation, not too difficult at all, to compute the pressures as a function of time. Then different components, like if I go back to this first slide, like direction valves and other kind of components, they will be modeled as a throttle, simple throttles, which I'm going to show you in examples in a second. And then the flow is traveling through these components, throttles, back and forth, and that's how it goes. All the components, pretty much all the components are modeled that way. So that's in a nutshell, lamp fluid theory. But I'm sure you did not get the whole, like, what? Like how exactly you use it then? Let me explain it. So let's practice. Here's a hydraulic damper. And in this hydraulic damper, I have cylinder here. And then I have here a piston rod that is going through this cylinder in both ends, here and here. And then I have here a piston. And in the piston have holes where the flow can travel back and forth. The flow rate can go and go from this chamber to this chamber. Now, how is that I can possibly model this by using my lamp fluid theory? Well, the first thing to do is that I need to divide this damper to volumes where I'm assuming the pressure to be equally distributed. Okay, so how is that I can do that? Well, I know that the pressure, if I'm changing my color here to make this more visible, pressure in this corner most probably it's going to be the same that the pressure here and then the pressure there. So obviously I can make an assumption that in this volume I can say that the pressure is equally distributed. Okay? But what about the pressure here? Can I say that the pressure here and here are equal? No, I cannot. Because it could be the case that somebody is pressing this piston or piston rod downwards, and that will lead to consequences that the pressure here will increase, pressure here will decrease. They will be coming back to be equal after a little while, because the flow here will try to compensate and equalize the pressure difference. But there are certain moments that the pressure is not going to be the same, but they are significantly different. That's why to model this kind of damper, I need to use two volumes. The one that is associated to this side of the piston, another one that is associated to this side of the piston. What's between here is a throttle where the flow can travel through. And you know that in a real dampers, they could be the sim plates and others. So this one here is not necessarily a constant, but it could be something that is changing as a function of pressure and other quantities. Anyways, the flow is traveling back and forth, trying to equalize the pressure difference. That's what you need to do. So it's pretty straightforward. So the first thing is like discretizing. Take your hydraulics circuit, discretize that to volumes where you can say that here within this volume the pressure is equally distributed. That's it. Not too difficult. Okay, so let me clear this. Okay, here is a real hydraulic circuit. The previous was not the really real one, but here I have a hydraulic circuit. That's the way that I'm assuming that there's a pressure source. So it could be a pump, but the pump usually the pressure could be changing a little bit as a function of time. But here I'm assuming that there's a pressure source where the pressure is always constant. How you do that in a real life? I don't care how you do it in real life, but let's just say that there's a pressure source. It could be, let's say, 150 bars pressure source. And then I have here direction valve. A direction valve has a 3 operation conditions. And now I'm selecting the one that is shown here. And I think that I need to take my drawings off to make this more clear to you. Okay. Then right after this direction valve, there's a hose or pipelines that is connected to this counterbalance valve, this one here. Now, if I'm modeling this hydraulic circuit, I can say that the pressure source, which is described here, is the one kind of like place where I need to take pressure into account. Not much to compute it, but just take into account, because I know that it's going to be all the times having the same pressure, 250 bars, simple like that. But then I have this place here, which is a hose line. And in this hose line, the pressure can be, whatever, in theory, pretty much whatever you want as a function of time. Of course, there is a physical limit what it can be, but it can fluctuate. It can change as a function of time. So this is a second volume where I need to compute the pressure, and I need to take I need to create the first order differential equation for that volume. Okay. Then I have here this counterbalance valve with a lot of pilot lines. I don't care about these pilot lines. I'm going to simply assuming that there is a simple throttle here that is describing that valve. All right. But what this counterbalance valve will do for sure is that it will introduce the pressure losses. And for that reason, pressure here, this part here, cannot be assumed to be equal to the pressure here. So I cannot do that. So that's the setup that I have here. And now this one here is computed by using then this pressure here. Then in a way back, from the piston rod side, again, I have here this volume, and I'm assuming that the pressure here, here, and here is equal. So they're equally distributed. That's why the pressure waves, I cannot take those into account. Then I have this direction valve, which again is modeled by using this simple throttle, which is a function of, or can change its size. And then this one here is a tank. So this is it. So really the tank is another thing that I'm assuming that there's a constant pressure, let's say 2 bars. So to compute this kind of hydraulic circuit, I need to have 1, 2, 3 volumes where I need this differential equation. And there are 2 additional ones which are constant as a function of time. That's it. So not too difficult at all. So that's how it works. Now the next step is this, that you need to practice yourself to do this discretization. And then you need to be able to create that differential equation we need. And then once you have that, then you're done. You have pretty much everything that is needed to do the modeling of hydraulics. But let me ask you this. Now, this is going to be a great challenge. So if I'm going to have hydraulic circuit like this, pressure source and tank, direction valve, which is different than in the previous case, and the hydraulic cylinder, which is different in the previous case, which one out of these options you can use to model the hydraulics? So which is your discretization? And now you just need to read it by yourself because I cannot read this for you. Let me put the Socrative on. Okay, and the question is that in love fluid theory, hydraulic system below can be modeled as. Then select the one that is correct. Now, if you're going to score 100%, I promise that there is a dance. For sure. Because this time it's not going to happen. But how is your guesses about the success rate? So let me see what's going on here. I started to get answers to my Socrative, but no comments about the success rate yet. I guess they are coming a bit later. And now I'm going to take a look at about what is that you guys said about the dancing. You were voting that dancing. And the game is on. Game is on. By the way, while you think about this, the one thing that I found it to be very useful, and I'm not sure if I mentioned this to you earlier, but when watching my recordings, it makes sense to put the closed capturing on because it's amazing that it can write pretty much everything correctly. So it really helps to understand. Subject matter still not helping in that regard, but otherwise it helps to understand my speaking. Let's put it this way. Okay, now you don't believe it by yourself anymore. So no one is saying 100% anymore, but much less than that. Okay, so let me send the Okay, so that's about it. So let me just check that it goes well. All right, so let me see. 46 answers already, so soon I'm ready to take a look like how it is. And no one, absolutely no one, let me just double check that, but it looked that no one is saying that it's going to be 100% today. Yeah, no one is saying 100%. Okay, and next, by the way, next story is going to be very exciting because I'm going to tell you how is it you can get this first order differential equation that describe the pressure as a function of time. Oh yeah, so there's a question about the second midterm exam, so I can answer that too. But let me first put myself back here. And we got the 54 answers. 54. Okay, but I think at the last time I took it was a little bit higher than this. Not significantly, but a little bit higher, like a 58 if I remember correctly. So so while you guys thinking the next midterm exam will be in December. That's right. It's going to be open in December, and I'm going to do it in a way that once we're done with the lectures, then I'm going to put it on. So I will give you 1 week time right after the first, right after the last lecture that you can enter your answers. And this time the midterm exam is easier because the subject matters are related to hydraulics and other things that are not that complicated at all. So it's going to be okay. So it's going to be very much okay. Okay, now I got the 55 answers, and this is how it look. Success rate in this case is how much? My guess, 75. 75. Okay, 45. So this was a catastrophical success rate. All right, but that's okay because the last time we did so well. All right. So first thing to do here is that we need to understand that this is a one way cylinder. The cylinder that is operating only in a one direction, so there is no pressure in the piston rod side. So all these components that there's like two different channels, which is this one here, just one, is off the picture. This cannot be the correct one. Then you need to also understand that this hose line is connected to this hydraulic cylinder. And in a similar cases like this previous slide, so we can assume that the pressure here and here are having the same numerical values. So basically you need just the one volume to compute the pressure here. One, not two. So that's why this is off the picture. Definitely you don't need three. So the only one left is this one because you need to have just the one pressure to compute it. That's it. So just one differential equation will do it. And now there is a one celebrating that just hit the spot. You're right. You hit the spot. You got exactly this correct. So exactly correct number. So good job. Let me. Where the heck is my notes? Um, where is it? Uh, there. Nice. Okay. And now what follows is that I'm going to explain you how is that you can get this first order differential equation needed to compute the pressure as a function of time. Okay. Um, so let's make a setup experiment. Maybe the experiment is a better word. And I'm going to take a look at the piece of volume or piece of hose here. And I'm putting the material flow in this pipe or hose. And then there's a material flow that is leaving from the hose. Okay, so again, I have here material flow that is coming in to this control volume or hose or whatever you wanted this call. And then there's a mass flow that is leaving. So coming in and leaving. There is a two correct cases. You're right. You're right about that. So there is another one too. Nice. Good job. You guys need to do lottery. Okay, material flow in, material flow out. And what's in this control volume is a mass. And this mass, or kind of like a material flow too. So there is a certain kind of steady material flow. So this is my setup here. Now what I would like to do here is that I would like to measure how much mass I have, fluid mass I have in this volume, this control volume. I know that the mass can be computed simply like such the way that is a density multiplied by volume. Okay, so it's very simple. And this is a volume that we're looking. So this volume is the one that we're looking in this control system or this experiment here. Now the mass can change if there is a difference between the mass rate in mass flow in, mass flow out. So if this is not having the equal amount of mass flow coming in and leaving, then there's going to be difference in the mass. Such the way that is, if there's more material coming in, mass becomes to get bigger, increasing more clearly. Or if there's more leaving than coming in, mass is decreasing. So this is the math that we need here. So not more complicated than this. You see, this is what we are already here. So this is our differential equation because this can be expressed. This is m dot. Okay, but the mass is not the good quantity to compute it here. Sorry that I'm plugging the view. Saying here m dot. How much the mass is moving or changing as a function of time. So I need to use a bit more advanced mathematics to make this to be useful. And I'm sorry, for some reason I have placed the text in a way that I'm a little bit blocking the view. Okay, so let's use the previous equation and let's replace the mass by density and volume. And then this is it. Now, we could do this mathematical operation, and it is already made here. So I can do this differentiation. First, I differentiate this density, and then I will differentiate the volume as well. Okay, so this is how it looked like. Now, I'm going to make an assumption. And in my assumption, and I am assuming that the flow density is same in the incoming mass rate, mass flow, and leaving mass flow. And if I do that assumption, I can simplify my equation as it is shown here. So it's getting close. It's getting close what I need. But I still have this problem because I have this density P. So I don't want to use this P. I want to have a P pressure, not density. How can I change that? Okay. Well, I can use a little bit of mathematical skills. So, this is coming, by the way, from this equation that d V divided by d rho is V multiplied by rho. So what from this equation and using the definition of bulk modulus, I can express this relation which is a relation between the density and the pressure here. Density and the pressure. Okay, so I'm almost there. So I'm going to substitute that information to my previous equation, and it looks very promising because look what I have here. I have a pressure as a function of time, and then a bunch of other components. Like, this is how the volume is changing. This is my bulk modulus, effective bulk modulus. Great, I already know what that is. That is the one that is describing, yes, flexibility. It's describing the flexibility. Okay, so then I just take all these components other than the p dots, right-hand side of the equation, and this is my differential equation. So I have here p dot equal then bulk modulus, describing the flexibility, divided by the size of the volume in question. Then I have here flow rate in, flow rate out, and how much the volume size itself is changing. This is not usually not necessarily the case. But there are certain components where the volume size is actually changing. One of the common ones, which I'm sure you guessed already, is a hydraulic cylinder. So in a hydraulic cylinder, the volume difference or the volume change as a function of time can be accounted by using this component here. So this is all that I need to know. These are all the components that I need to know. So this is it. So So this, is mentioned here that, this means in practice that is a motion of a piston. So yeah, that's right. That's what it is. Here's my first order differential equation, and that's it. Look about this was the hardest mathematics involved to hydraulics, and it wasn't too hard at all. And we were able to get this first order differential equation. And now if I take ourselves back to this slide here, how is that we can compute the behavior of this damper? Well, it's going to be pretty simple then. So we're going to compute the pressure here using this equation that we just learned. Again, the pressure was a bulk modulus divided by volume. Flow rating, which is, if the flow is going here, it have to be minus sign. And then the one that was minus the piston motion. That's it. And this have to be P dot. And the same here. Here, of course, I'm sorry, I'm blocking the view, so I'm going to put it here. So it's going to be like this. P dot, effective bulk modulus, volume size. And then the flow here is have to be positive in a sign because it's coming in here. And then this one. That's it. Those are my pressures. And what I will do with the pressures then? Well, I need to get the pressures because the force then produced by this damper, or damping force, or hydraulic force, is then computed simply by taking the pressure and corresponding cross-section area into account. Now this goes, if this is 2, this is 1, so this is going to be this one here corresponding this cross-section area. These are the one that is corresponding this one, and then the ones are P1, PA are the one that is corresponding this one. Very messy, but hopefully you were able to follow me. So now let's go back here. So let's move our result back here. Yeah, the next in-class quiz is going to be difficult. It's going to be difficult, but remember, this is what we're doing. So we are dividing the hydraulic circuit within the volumes where we are assuming pressure to be equally distributed. What that means in turn, it means that we cannot take these pressure waves into account. All others we can take into account because in my next in-class quiz, I'm going to asking what is that we are ignoring, meaning not taking into account in this equation. We are ignoring, well, I'm not going to say it in a clear way, but I'm saying that we are assuming pressure to be equally distributed within the volume. So there is a certain consequences of that. We do take a effective bulk modulus flexibility into account, and we do take the volume change into account. So with that instructions, or with those instructions, so let's move on to next in-class quiz. And the next in-class quiz is going to be this one. Now I got lost about, here, finally. Okay, lump fluid theory ignores something. And the options are pressure waves within the hydraulic volume, change of the size of the hydraulic volume, physical size of the hydraulic volume, compressibility of hydraulic volume. I want to make your life easier, so I'm going to write this equation. So this was an equation that was based on this lump fluid theory. So take a look at these components and think about it if it is there or not. And if it is there, then it's accounted. This is, oh my God, my handwriting is so unclear, but this is we. Okay. So what do you think? What are your thoughts? And there is one more story that I'm going to tell you today, and it's going to be simple. It is about these flow types. And let me see, we still have like 25 minutes to go, so we'll see how it goes. And then the components, I think I'm going to leave for next week. All the components, but we'll see. We'll see how it goes. Okay, so a game is on, and I got the 40 answers at the moment, and a lot of guesses. This time the numbers are a little bit high. So there's even a good friend of mine is guessing 97. Maybe that sounds a little bit high to me, but maybe it's okay. And then others are saying like 76, something like that. Yep. All right. Maybe remember the last time the ones that were really good ones. Maybe you want to follow them as well. Maybe you want to take a hint from those ones. Okay, so I got now what happened? I got much less answers, so 48 answers so far. And when I'm looking the number of views, that number still shows me that is a 53, 53. Okay, so we'll see. All right. Now I got this same number that in my view, so it's a 53 answers in my socket, even 53 views. So let's close it. Let's close it. So here's my okay, and now I got one more, so 54. All right. So let's see how is the weekend doing. How is the week doing today? Let me see. This is by the way the last in-class quiz of today's lecture. So we'll see. And here is the success rate. Ah, so it's good, really, really good. So we are not taking the pressure waves in hydraulic volumes into account. So we don't do that. Why? Because we are assuming the pressure to be equally distributed. I repeated that number of times, very many, well, many times actually. So that's what we're doing. And other things like the pressure, I mean, change of the size of the hydraulic volume. It's the one that is here. This one is accounted. Physical size of the hydraulic volume. It's this one here. So it is accounted. Compressibility of hydraulic volume. Excuse me, hydraulic volume. This is the bulk modulus, so it's there too. So all others are counted. So the only one that is not accounted is the pressure waves. And we say, or we assume that in a mobile application, so they are not so significant. Really hard, case dependent. So I cannot say for 100% sure that it's always something you can ignore. Keep in mind that this is what you're ignoring, and that's all you need to know this time. Okay, and as I promised, so one more story today, and this one more story is about the different flow types. And now comes, something that I'm sure that many of you are happy because we're gonna look at that, particles. And oh my God, particles will whirling. I don't know if it is rotating, but it's whirling. So I'm sure you're happy to go back to the particles. So flow types is next. And the flow types, this is not going to be that complicated topics because we have two choices. Two choices. These choices are laminar flow and turbulent flow. And before we jumping into this topic, let me describe it. What is the deal with this? Okay. So let's say that we have a hose here, and then we have a throttle here, which introduces the pressure difference. Or the pressure difference, or the flow rate through this throttle is tried to equalize the pressure difference in both sides of the throttle, however you want. This is a little bit like an egg and chicken situation. Anyway, so we have a pressure P1 here, and then we have a pressure P2 here. Flow through this throttle here can be computed as a function of the pressure difference. And the pressure difference is very simple, so it's going to be computed like this. So it's a pressure 1 minus pressure 2. Now, how the flow, this one here, is a function of the pressure difference. This is in a modeling perspective telling you what type of the flow we're discussing. And like I said, we have two different choices. We can have a laminar flow, which typically takes place when the pressure difference is small. And what that means? It means that when this pressure difference is, let's say, less than, I would say, 5 bars, this is a rule of thumb, then it's a high chance that the flow type is a laminar flow. And in laminar flow, the particles, these fluid particles are traveling with a good agreement. They have no disagreement whatsoever. How it look in real life? It look like this. The flow or the path of a particle look like this. So it's like a little bit of traffic jam here, but there is no accidents or anything like that. So here, kind of the particles are simply compressed, but they're still in a good agreement. So this is how it looks. And again, this takes place when the pressure difference is small. And when the pressure difference is high, then it looks a little different. Then it's going to be turbulent flow. And in turbulent flow, particles are not in agreement anymore. And the traffic is not smooth. Because right after this throttle here, there's a whirlings. Okay, you can say that if this makes you happy, you can say that there's a particle rotation. So the particle is rotating. It's not really is rotating, but it's whirling there. And this is how it look. If you take a microscopic view about the turbulent flow, this is how it is. And this is a second particle and others, and they have this kind of whirlings here. All right, so this is the flow type here, which is called turbulent flow. What's the difference in the modeling wise? Well, the difference is pretty significant because the flow rate here and the pressure difference can be linearly related or quadratically related. In a turbulent flow, the one that is shown here, they are quadratically related. So this pressure difference is under the square root. And then there is some kind of like a parameter that is telling you how is exactly this dimension of the throttle. So, but roughly this is how you can model it. Whereas in a laminar flow, you still have the flow rate and the pressure difference related, but this time it's related in, let's call this again the parameter, which depends on the physical dimensions and such. This relation is linear relation. And you can see that clearly when you see measurements made of the hydraulics. So if the measurements, I don't know if maybe I should go to the next slide here. Let me try to show it here. So if you have a curve where there's a pressure difference and this is a flow rate and they are behaving like this, you can tell immediately that this is something that is a turbulent flow. And if it is behaving like this, then this is a laminar flow. So this is it. That's the difference. Linear or quadratic difference, or linear or quadratic behavior. Okay, anyways, there are ways to define which is what, when the laminar flow takes a place and when the turbulent flow takes a place. In a modeling perspective, particularly in the mobile machinery, it's not critical decision because, again, like I said, pressure difference, when pressure difference is small, 5 bars, then it's laminar. It's an unusual case that you can easily find without modeling the laminar flow at all. So you can assume that pretty much all the throttles having the flow which is turbulent in nature. Okay, but if you want to do it well, this is a little bit about how the particles is moving. So is it smooth or whirling? So these are the different scenarios. And I was about to say that you can easily model all these throttles by using this turbulent flow. So that's kind of safe choice. There is, however, one numerical difficulty associated with that selection. And the difficulty is the fact that, because we're using this tangent computing all the time. The tangent is a problematic here when you're approaching the zero pressure difference. Because then here the tangent, here the tangent is like this, here is like this. But in the close to zero, the tangent goes to infinity. So it means that the numerically is hard to understand the fact that in a zero pressure difference, the flow rate is zero. This is something that is kind of hard to understand if modeled by using this turbulent concept or framework. So what you can do then is that you can assume that in a very small pressure difference, there's like linear regime here. And in the linear regime is something that helps you to perform this numerically more efficiently. Okay, anyways, so how is it I can then define what is what? I can use something that is called Reynolds number. And the Reynolds number is something that you can compute it, and then you can compare the Reynolds number to something that is called critical Reynolds number. And that's the decision making you need to do if you want to really make it this sophisticated. But typically in a modeling, this is not really made this way. Okay, so it says that the flow is laminar if your Reynolds number is less than critical Reynolds number. The critical Reynolds number is something that there's a pre-calculated tables that you can compute. You can compare your Reynolds number against that. And if it is more than the critical Reynolds number, then it can be assumed to be turbulent in nature. Okay. So how is it you can compute the Reynolds number? Well, you can use this equation here, which is not clear at all because, I can see that the kinematic viscosity and the velocity flow of the flow is not clearly recognizable. Hold on. So this is velocity. This is kinematic velocity. Kinematic viscosity. Kinematic viscosity. My mistake here. So this is kinematic viscosity, and this is velocity. Oh my God, it's so unclear because the notations are looking alike, so there's like absolutely no difference. And there is a hydraulic diameter, which is a hydraulic diameter, a little bit different than the physical diameter. But if you want to learn the details, take a look at some of the handbooks about the hydraulics. But again, this is something that is less critical for us because, we can easily model everything by using this assumption of turbulent flow. Okay, but again, how it goes then. This is pretty much what I just explained to you. So in the case of laminar flow, which again is a function of viscosity, and I'm going to show you a couple of the pre-calculated tables next week. So just to make sure that I kind of demonstrate that how it goes in a real life. So in the pre-calculated tables, you can get this coefficient. Now it's called CL. Previously, I used something else. But again, it's just a coefficient that you can get it from the pre-calculated tables in a way that I'm going to show you next week. Okay, but again, the big important thing is here that the flow rate and the pressure difference are linearly related. Okay. Then in a turbulent flow, you can see that they are this quadratically related, and now this is now more advanced equation. So I have here discharge coefficient, which depends on the geometry of the throttle here, and then I have the cross section of the throttle, and then square root 2 divided by density, and then there's this pressure difference under the square root. So that's how you compute it. But again, the important observation is this, that the pressure difference and the flow rate is quadratically related. That's what you need to know. Okay, so now we start to discovering and looking at the different hydraulic components. And this is a list of components that I would like to explain to you. And here I'm going to take this chance that I'm going to explain you something a bit more advanced in terms of hydraulics. So I'm going to explain you about, what are these recent developments concerning the digital hydraulics. How are the recent, well, they are not recent developments, but advanced pump technologies. How is it you can possibly save a little bit of energy by having a bit more advanced pumps? Because pump is the one that is producing the energy to system. And then you're kind of losing the system, and that's how it works. And if you keep on producing the energy to the system regardless of the need of the energy, then your efficiency is not going to be very high. And this is exactly the problem in a conventional hydraulics. A little bit of problem in a modern hydraulics as well. Okay, so the list of components that I would like to cover in this course is a throttle valve, direction valve, pressure relief valve, which is just for your information, not particularly important, cylinder and pump. That's it. That's it. So there are two different kind of valves, and the one valve is the one that there's no moving components. I'm just assuming that there's a throttle, and that the big kind of important component is direction valve, because that's what definitely is used most of the common or practical hydraulic circuits. Okay, so component modeling, and I promise that I'm gonna close this uh, right after explaining the flow rates, but I see that I still have a couple of minutes left, so I'm gonna use this opportunity to shortly explain about the modeling philosophy associated with the different components. So the modeling philosophy, it's such that we could, in theory, have three different approaches to model the components, three different approaches. And these approaches are then explained in my following slides. Well, first of all, these are prior to these philosophies, I would like you to be aware of that in a component modeling, we kind of have two steps. And the first step, we are modeling the moving component or the location of a moving component. So what are these moving components then in hydraulics? Well, they are typically spools or puppets of different components. Like here is a pressure relief valve. This is how the pressure relief valve look like. And the pressure relief valve, you have this spool. That is, the spool is this component. The spool can go up and down. And if it goes up, then it opens the throttle such the way that the flow can travel through this corner here. And if it is closed, then there is no flow whatsoever. So the first thing to do in the hydraulic or the component modeling is that you need to figure out the position of the spool. And once you know the position of the spool, then you can estimate how much is a flow rate through this component. So two steps. Now, this kind of like approach can be accomplished by using three different scenarios or three different philosophies. And these philosophies are based on, or kind of like they are either empirical models or analytical models or semi-empirical models. And what we're going to use in this course is going to be, of course, the one that is combining the empirical models and analytical models, and that's the one that is showing. Oh my God, where is that? I got lost. Oh, where is it? Semi-empirical models. So empirical models, analytical models, and empirical models. And I can see that I'm kind of running out of the energy today because my explanation becomes to be chaotic. Sorry about that. So let me just explain about these three different philosophies, and then I will let you off the hook. So I'm going to close today's lecture, and I will see you in a team session. So shortly, definitely final thing to explain. What are these different philosophies? Empirical models are the models describing the different components such that everything is based on measurements. So you do an awful lot of measurements and you're building pre-calculated tables, lookup tables, if you may. They can be also put in the form of the neural network, or if that's what you prefer to do. But anyways, there's an awful lot of measurements that are put it in a table. And then you just take the values from the table, and your components is considered as a black box. So you really don't know how it behaves, but you know what is a numerical value that it is introducing. So that's it. So empirical models are requiring a lot of measurements. And because we here in this class and other classes that I'm responsible of, we prefer these numerical approaches. So we are not a big fan of this. So we don't want it to do an awful lot of experiments. For sure not. Okay, what is the other extreme? Other extreme then. Analytical models. Analytical models are something that you're modeling the spool position and the flow rate by using pure analytical approaches. This sounds like way to go, but there's a big problem. And the big problem is that these analytical models requires an awful lot of parameters that you probably don't have. Example is the spool weight, a mass, spool mass. Do you really know how much is the mass of the spool? Typically, this is an information that the manufacturers are not giving to you. It also needs an awful lot of information about the detailed geometries, which we probably don't have because the manufacturers are unwilling to release that information. So what is left is a combination of these two. So we can combine experimental models and analytical models and call them as a semi-empirical models. Idea is that we get started from the analytical models and we're converting these unknown parameters to be in a form that we can get them easily from the manufacturer's catalog. That's the idea. So getting started from the full model, then converting it, manipulating it a little bit, such the way that the unknowns can get from the manufacturer's catalog. That's the way to go. That's what we're going to follow in this course. And with that, I'm going to close today's lecture and I'm gonna visit in the toilet and I will see you in a minute in a team. So come and celebrate this 100% success rate with me to team session, which will get started after a minute. Okay, so I'm gonna close this streaming and I'm gonna end this end the recording as well. So see you soon and see you next week in the same place.